Hi guys, so I'm making this video to try and save some time in class because I already got to pause it because I forgot to wire up my tablet. Okay, I'm back. Well, I'm sure you didn't notice a thing. Okay, so I'll be printing up this lab manual for you. Let's see, it's not completely on the screen for you guys. And so I'm gonna go over some of it. So hopefully we can get a faster start. So all oscilloscopes have all these four things among others, and these are very simple oscilloscopes to try to not scare you quite so much, I suppose. Some of them can be pretty intimidating looking, but this one is basically stripped down to the barest essentials. So there's always a section for the beam, the trace that'll come across the screen, and to focus it, change the intensity. What you'll notice is that at various times, at various settings, the display will be brighter and darker, and we always want to watch and see how bright it is. Basically, if you have a trace across the screen and you see a halo around it, you have to lower the intensity because this is an old style TV screen and it's got this chemical on the inside, this powdery stuff, fluorescent material. And just as you saw in the pre-lab, the beam hits, there's an electron beam that hits it and then scrolls across. And I said beam, yeah, trace is the better word. The thing goes across over and over. And we don't want to burn holes in the screen. Then, let's see. There is the triggering area, the green here. So I went through the manual and made sure that the instructions match up to the oscilloscope. In the past, we've had mixed different ones, but we have for you guys all the same. And this is, you'll see this referred to, the trig level knob. This can be pushed and pulled in and out. And then when you hear about coupling, it's either going to be AC or line. And then we're going to trigger on channel 2 and perhaps external. And then when it says something about the slope, that's this button. So when it's out, it's plus. When it's in, it's negative. And you'll see what that means when you play with it. And triggering is not super important for us. We're going to go over it so you see what it does. So now, the heart of it is that this is a 2-channel. So these things control the vertical axis, the volts per division, or volts per box, these boxes. And they're sometimes referred to as volts per centimeter. They're approximately a centimeter. I say box, and they say divisions. And I'll get into it in a moment, what goes on here. And now when you see these, you can set the input to AC, ground, or DC. We're going to mostly use DC. And there is these little inner knobs, and you have to make sure that they're always twisted to the right and they click. Oh, never mind. I see what it is down below. They're not here. This oscilloscope is different. It has these variables here, and they have to be you twist them to the left. I see, until it clicks. Okay, then the other part is the x-axis Oh yeah, and then position knob moves the trace up and down. And then the x-axis is time. And as you may have noticed in the pre-lab, you can change how fast it goes across the screen. And yeah, we want to make sure this button is out. We're not going, but you won't remember that. But this XY mode we're not going to use. And this button has to be pressed in. I've been editing the manual. I see where it needs even more additions to it. But anyways, this removes the trace left and right. But the key here is the number of seconds per box. And this one does have a knob in the middle. We want to just keep it twisted all the way clockwise until it clicks, and it's gentle because you can break internal plastic. All right. Now, basically, oscilloscopes are all about, and I'm going to duplicate this just in case I need another one. Oscilloscopes are all about making a pretty picture. So they're extremely generalized. So your pretty picture means that it's vertically as large as possible. So you do that by twisting the volts per division knobs so that it's as big as you can get it without going off the screen. And then horizontally, you want at least one wavelength. And it's usually better to have like 1.5 to 2. And you see what we've got here, if we were to start here, we've got 1.5. But what I mean, it's better to have two to three peaks. So you want to make sure that there's nothing, you absolutely know nothing's funky going on. Although, once you could in principle switch it, but once you establish that your trace shape looks fine, then it is easier and more accurate to get the timing by having only the two peaks like this. Okay, so let's see, how do we measure the time? And you may already have heard this, and I'll just go over it again. So the period, that's what capital T is. So we set the first peak on a convenient vertical line. And we're going to find that our oscilloscopes, if you look here, you see they have these special lines in the middle. And we'll go over this again in class. So you find a convenient vertical line, a grid line. And then what we're going to do is we're going to move the trace down to here, because then we can take advantage of those little marks. But the basic principle is we count boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this happens to be exactly 12 boxes. Then we look back here and we see, oh, this one, oops, no, here it is, 10 milliseconds per box. So we write 10 milliseconds per box. And then we see that boxes cancel, and we get 120 milliseconds. Oops, not physics 1100, which of course is also 120 times 10 to the minus 3 seconds. And to get the frequency, we just get the inverse of the period. Okay. The other thing is that now we want to measure the voltage. And you always measure V peak to peak. You never assume that you can know exactly where the zero is and try to measure amplitude. It's just not done. So when that happens, you see how they've done here. They've picked a convenient horizontal line, and then you would move it left and right so the upper peak is on this special line in the middle. We'll go over it again in class. So then we count once again. 1, 2, oops, on the wrong page. So V peak to peak equals 1, 2, 3, 4, 5, 6, 7, 8. And it looks like I'm going to just below half, so I'm going to call it 8.4 boxes. And let's look at channel 1, and it says 0.1 volts per box. See it here? So 0.1 volts per box. And they cancel once again, and we get 0.84 volts peak to peak. Easy peasy, right? All right, so that's, that once you master that, then you basically know how to use an oscilloscope. All right, and then again, you do this by twisting the time knob and the volts per division knob. And also, sometimes you monkey around with the trigger. We'll use auto triggering a lot, so it's not, you basically don't have to worry too much about it, but hopefully by the end of the period, you understand exactly what triggering is doing. Okay, so for the most part, you're going to just run through this thing, and you're just going to go section by section. Here we go. A, that's a setup section. Now you observe things, and you write down what you observe, and also you got these little grid patterns here, and you can cut these out and paste them in your logbook. You're welcome to simply make a picture if you want. This seems too cluttered, too busy. And you trace this out on your, you trace out what you see on the screen on these little squares. And then at the end, oops, then we're going to be filling in this data table. And we're going to use, well, what we're going to measure is V in and V DUT, which is the V out. I'm going to go over that now. And, and there's this concept of impedance. So I don't remember anymore what's in pre-lab. And so before we say anything else, what is impedance? Here it is. Impedance is just a fancy word for resistance, and we need it because capacitors and inductors don't behave the same as resistors. They're not ohmic, so capacitors and inductors are not ohmic. meaning they're not linear. But they do have a resistance. And it turns out that it's frequency dependent, which makes why they're so useful. And so for a capacitor, it's, oh wait, excuse me. I have to hit the undo button. For a capacitor, it equals 1 over 2 pi f times the capacitance. So you see, as frequency increases, the resistance of a capacitor goes down. And an inductor is 2 pi fl. So the inductor has the opposite behavior. As the frequency increases, its resistance goes up. And so the definition is some real part plus I times this letter chi, which is the reactance. So strictly speaking, that's what this is, the reactance. Because the two of them change things. They change value and they do things to the voltage and current. And what we do then is we can do that. We have the real axis and the imaginary axis here, and we can treat for example, this here becomes a vector, and I don't know how much of that. Well, certainly we don't need it for this lab, and I don't remember how much of it you need for Physics 1200. But if necessary, I'll have to review that, and maybe I can make a video that can help you out in the lecture. Okay, so this is definitely important. This for your notebooks, we have this business of the resistance as a function of frequency. That's important. And yeah, and the part about this imaginary number and the complex plane, that's not important. You just Z is just generalized R, really. And so also, what was I going to say? Oh yeah, Z is still equal to some V over I. And also, this also makes the rules of combination easier. So the rules of combination are the same as resistors. So, oops, run out of room. So in the case of, if I had, now here's the interesting thing, right? Well, maybe you don't think it's interesting, but I do. So this is C1 and C2. And so Z, we'll just say, instead of Z1, we'll just say Z1 and Z2. And so what's the Z total? Well, Z total equals Z1 plus Z2. But remember, that's 1 over 2 pi FC plus 1 plus 1 over 2 pi FC2, and it's 1 over 2 pi FC total. See what happens? And we can eliminate this because it's the same for each one. So there you see. That's it just makes keeping track of math easier, and so that's why impedance was one of the reasons impedance was invented. Okay. Oh yeah, what's VRMS? Well, you have that in your notes. Basically, the most important thing for us is that VRMS equals square root of 2 over 2 times V peak to peak. VRMS equals square root of 2 over 2 times V peak to peak, which is basically 0.7071 V peak to peak. Okay, so as I was alluding to, now we're at the end of the lab, and we're going to be putting the different devices under test, and we're going to measure, eventually measure the impedance of what's here, but we're going to do it by measuring V out over V in. And there's going to be 4 devices under test. There's going to be R experimental. There's going to be feature bloat. Then there's the capacitor. Then there's going to be an inductor. And then the last one is going to be the capacitor and the inductor in series. And it doesn't matter what order they're in. Okay, so let's derive our formula. So to make our writing a little easier, we'll call it Z1 and Z2. And notice this is very similar to what we've done before. The original manual, this ground symbol is just the black wire. You guys are going to be putting into the those connectors on the face are called BNC connectors, and you're going to have this adapter thing that's going to show you this. There'll be a red and there'll be a black banana jack, so it'll turn those are BNC connectors to banana jack. Okay, so the voltage out is going to be the voltage across Z2. So that means that the Z2, the voltage across the device, let's use our nomenclature. V2 is going to equal the current times Z2. And remember, this is a series circuit, R standard and the device under test, so there's no subscript. So what is I? I equals V in divided by Z1 plus Z2 . So we see that VZ2, which of course is the total across Z1 and Z2, equals V in times Z2 over Z1 plus Z2. So channel 1 measures V in, and channel 2 measures V out, and which also is the voltage across the DUT. And then our algebra here, it is V out, VZ2. And this is the classic two-element voltage divider equation, it turns out. And so, well, and this is the way it's done. It's always, the original manual has some funky setup, but we're going to do it the way the whole rest of the real world does it. And it makes it much easier to take data. So for each frequency, you're going to make this table in your books and pick a frequency. We'll have a list on the blackboard. And then you see, well, they're not in the same order, but the inductor, the capacitor, the resistor, and the series combination, you measure V out, V in, V out, V in, and that's V peak to peak. It didn't come across that well, but you have some frequency here, say 500, then V in, say, is 20, and we're going to say it's voltage peak to peak, so we don't put units in there. And the inductor might be, I don't know, 1 volt, because it's low resistance at low frequency. This one could be 20, this one could be 19, and etc., etc. And as I say in the text of the manual, what you do is you set a frequency and then you measure each device. That's the fastest way to get data. And that is what you need to take home with you. I wanted to talk to you, and most especially in this, about the formula here, where it comes from, and you can see that it already looks pretty kind of similar right there. So we'll copy this and we'll paste it. So if we cross multiply, this becomes V out times Z1 plus V out times Z2 equals V in times Z2. So we want to isolate. So let's get Z2 on the same side. So we have V in Z2, and I'm just going to write an I there instead of in. And then I'm bringing this one over to here. That's a minus. Oops. Yeah. V out times Z2, and then this one is over here. V out Z1. And then we see that we can pull out the common term. And V out Z1. And so we see that Z2 equals Z1 times times V out divided by V in minus V out. Now, we translate that into to our setup, that means that the Z of the device under test equals the R standard multiplied by voltage of the DUT and divided by V in minus V DUT. And that's where, that's where that comes from. So I remind you that tomorrow, all you're going to do, well, in lab class, who knows when you're going to read this, your job is to fill out this table. And as I mentioned in the manual, when you make this table in your logbook, well, I mean, you're not going to make bold-faced lines like this, but you want to have some, we may do more frequencies than that. I have to go up and check the values of the capacitor, the resistors, and the inductor, and then I'll plug it into my spreadsheet here and see what frequency range we need to use. It looks like maybe we can get away. Is that 8 points? Well, we don't. 1, 2, 3, 4, 5, 6, 7. We are not going to do any fitting. This is one of the few times when you connect the dots. So you see here, oh, you can't even, I'm talking about something you can't see. So V, that's the V out, that's the V in. This is the old style. Okay, so I'm not going to talk much about this particular detail, but so you see here I plotted the measured ones with the dots versus the calculated ones that I put to see how they compared. And you'll notice, as predicted, the inductor starts low and gets high. The capacitor starts high and gets low. Data's a little funky. And the resistor stays constant. And then the LC circuit shows this kind of, it has two wings, so it's sort of like a teacup potential energy function. And it's these behaviors that make these things interesting and useful. Okay, I think that, wow, 33 minutes. Oh, I was speaking slowly. Oh yeah, and then just, going to be using this function generator, but I've made, well, in this case, it's here and it tells you exactly what to do on all the buttons. And then, I'm going to provide you with some pictures to cut out and paste if you like. And at the I'm not going to print this on every single one, just on the chance that somebody has a different one or the other. Function generators have this cheat sheet, and then we're not. This is a digital scope, but I don't think we're going to be using that ever. We'll see. Okay, get this up to YouTube.